Good morning to everybody. This is an IC session. The topic is artificial intelligence based management is a fast reflecting the conventional approach in ophthalmology, recent facts and future. Yes. I am Dr. GOPAL Agrawal. I am the chief instructor, and my co-instructors are the Dr. Aditya Anand, Dr. Abhishek Anand, Dr. Devesh Kumawat, Dr. Pranita Sai, Dr. Pranav Ranjan, and then myself, and then Dr. Sujit Kumar Mishra. Just to start with, next slide. Next slide. Yes.
Next slide, please.
Yes. First presenter is Dr. Aditya Anand. He is MBBS from JSS Medical College, Mysore, then post graduation from RIO Minto Hospital, Bangalore, and then DNB student at present DNB students at Arvind Eye Hospital, Pondicherry. Presented papers, poster at state level and national level conferences. Key speaker of artificial intelligence in IMA in 84th IMA conference Medicon in Bangalore. Just start Dr. Aditya Anand. His topic will be as an introduction to artificial intelligence.
Hello. Uh, Good morning, all of you. Uh, I will be presenting on the basic introduction of artificial intelligence. So, coming on to the topic, so what is artificial intelligence? It's a simulation of human intelligence processes by machines, especially computer systems. So, basically, these processes include learning, reasoning, and self correction. So, how does the learning is the acquisition of information and rules for using the information, and reasoning is using rules to reach the approximate or definite conclusions, and self correction is the self validation. So these are the processes which is included. So basically artificial intelligence, people think that is it a hype or reality. Basically it is showing a greater growing interests for from all the organizations. So every industry wants intelligence, so whether it's medical or any other sector. So organizations engaged with NVIDIA or deep learning, so these are gradually increasing year by year. So the big players in this are this Amazon, Facebook, Google, IBM. So everything is getting ahead on this technology. And in the big players, startups, a lot of startups are also there, especially this MetaMind and Deep Instinct, SkyMind. So there are a lot of startups coming gradually years by year, and everyone is working on artificial intelligence. Recently, the Gravitas have also started on this. So the components of artificial intelligence, how does like it covers basically all the knowledge, perception, natural language processing, machine learning, robotics, planning, neural networks, and cognitive system. So we will discuss ahead of in coming slides. So artificial basics is like it is the objective, it is to automatically detect and measure the pathologic features in images of the eye. So basically recognize the images and then it gives the results. So So here programmers give the software mathematical descriptors of the features to detect, and a rule-based algorithm for searching these patterns on incoming images. That is called as a pattern recognition. So these things which it recognizes correctly, it is called as positive hits. So positive hits are combined to produce a diagnostic indicator. Second is the basic machine learning. In this approach, the algorithm is given some basic rules about what disease features look like, along with a training set of images from affected and unaffected eye. So the algorithms examine the images to learn about the differences. So that is the basic for which the machine learns in that. Second is the advanced machine learning. So this type of machine learning consists of one or two interconnected layers of small computing units called neurons, which mimic the multi-layered structure of the visual cortex. So here, as you can see in this picture, there are a lot of inputs which is coming to the machine from various sources, whether in pattern, in images pattern. So machine learns itself in the supervised learning, and whether which images are correct or the positive hit comes, so machine learns itself to detect it as a correct image, and later on the on the subsequent search and subsequent recognition, it goes towards the more correct results. So that is how it learns to layer by layer, and outputs of the neurons in each layer feed forward onto the next layer for further analysis by the data of that layer, and the final layer yields the diagnostic output. Thus, the neural network learns to associate multiple specific inputs of disease feature detectors and results in more accurate diagnostic output. So now coming on to deep learning with convoluted neural networks, the term deep learning is used because there are multiple interconnected layer of neurons. And second is because they perform their task through repetition and self-correction. So this new approach leads to latest iteration, the software of artificial intelligence. Thus it comes closer to resemble thinking like us or thinking like humans. Okay. So there is a disease feature based versus image based learning. So in this, what we do is this till now the machine learning algorithm what we have discussed till now, it's a multi-layer data algorithm based on clinically known characteristic of disease, such as any kind of pictures, hemorrhages or exudate. So it is the supervised learning system. But now there is something called as like now what happens here, scientists is verifying, so whatever inputs we have given in the data learning system, or so these same image characteristic that a human would identify, the machine can adjust the algorithm if necessary. But however, the Google developed successful system called as Google Brain in 2016, but it is an unsupervised black box system. That is why how it adjusts the algorithm if necessary in this black box system. So the Google's deep learning algorithm here teaches itself to correctly identify diabetic lesions or photographs, though it was not, maybe it was not given as input like that, but the results they will give a correct, it's a correct result. So basically it is an unsupervised learning system which yields a correct output. So what's so exciting with deep learning is it actually scientists are not yet sure what and how the system is looking at. All they know is that it's arriving at a correct diagnosis as often as ophthalmologists are. Ultimately, so artificial intelligence will act as a complement to the skills of physicians. But unsupervised black box system unsettles some specialists with fear due to unsupervised approach. But definitely it will fascinate others because the results they're giving correctly, that too through the unsupervised system, so it can, even the non specialists can also get the results, correct results because of this. But however, it is not correct almost I mean many times it was not, it doesn't yield a correct result. So now this is a lesion, it's a graphical representation how does a lesion based disease detection and a black box disease detection gives its result. So lesion based disease detection, as I already discussed, is a supervised learning system. So images are given yield and everything, and then it detects the lesion, and then like lot of data inputs are recorded, and ultimately it recognizes the disease. But in black box this is unsupervised. So this is the technology of Google Brain which they have developed. And but you can still see that without any any data inputs, and that like it is giving a correct result. Okay. So coming on next, artificial intelligence is used for like what I mean, in many subspecialties it is coming into play. So the starting with this retina. So in the cases of ARMD, ROP, diabetic macular edema, diabetic retinopathy, all these cases, the artificial intelligence is going to play a major role. And these things will be discussed with with my next speakers. They will discuss these things in details, as well as it is a detection of diabetic retinopathy that AI is getting a huge role to detect the correct diagnosis. And as you know, this IDX DR device from IDX LLC was the first artificial intelligence in ophthalmology. So it was approved in April 2018. So this is basically, it is for the diabetic detection, all these things. And these things all will be discussed in details with my consequence speakers, as well as ROP, ARMD, as I already told, corneal topography, even in IOL power selection, and glaucoma. All those things are artificial intelligence is having a huge play. And this even now artificial intelligence algorithm, it can detect prior disease, heart disease, by looking at your eyes, by analyzing the patient's fundus, and how it does so, we will learn consequently. And even with the same accuracy as the current leading methods, it gives the results. So the limitations here is, though the limitations will be discussed in detail, I'll just give a brief out. The thing is that the quality matters here, the quality of the images, the problems with the image quality, the black box dilemma. Sometimes this black box dilemma will give the wrong answers. So these things are the current limitations of artificial intelligence. That there's, and the major problem of false negatives also comes, because sometimes that there is something called as it alters the image process, which is known as adversarialization. So in this, what happens is, like, the algorithm, which is, even if it is given correctly, so the in some inputs get changed and the results differ. So these things can happen. So now finally, coming on to conclusion, so what I find here is artificial intelligence is definitely a huge role in research for hypothesis generation, discovery, but definitely it's an augmentation, not a replacement of specialists. So final decisions and management will depend on specialists. Automated systems can and should complement what physicians do. Machines can only help the doctor make a better diagnosis, but they are not good at making the medical decisions afterward. So basically, the everything rests on the doctors itself. And current Indian scenario, Arvind, LV, all these institutes, and AIM, central institutes, and all these institutes are using this technology into play. And whatever be the pros and cons of AI, it is going to play a big role and will fuel a medical revolution in next 10 years by enabling far more efficient drug discovery, diagnosis, and research. Thank you.
Thank you, Dr.
Hmm.
Aditya.
Hmm.
Now, next speaker is Dr. Pranav Ranjan, who will be speaking on the current landscape of artificial intelligence for detecting glaucoma and its progression.
A very good morning to all of you, and thank you, Dr. GOPAL Agrawal, for giving me an opportunity to be a co-instructor in your instruction course on artificial intelligence. I also express my gratitude to the scientific committee and the All India Ophthalmic Society for giving us a platform to speak on this topic. So, artificial intelligence in glaucoma, it is one of the important um, factors which has come into play in the recent years. As we know that the open angle glaucoma is the most common subset of glaucoma, with around 53 million cases worldwide. And these are the tools which are taken into account for artificial intelligence, for giving an input data to create a pool of data for artificial intelligence. The optic nerve is just like a telephone connection between the eye and the brain. It traverses most of the part of the brain. So, the importance of the optic nerve and the brain and the eye, they are all very important. The eye diseases in which the artificial intelligence is being used widely today is the diabetic retinopathy, glaucoma, age-related macular degeneration, IOL power calculation. Apart from that, ROP, retinal vascular occlusions, keratoconus, cataract, refractive errors, retinal detachment, strabismus, ocular cancers, they also are being included in artificial intelligence category. So why artificial intelligence is important in glaucoma is because of screening, early detection, diagnosis, classification of glaucoma, quantifying the risk factors, and also looking at the progression. As we all know that glaucoma is typically a asymptomatic disease in the early stages, and detection depends on the clinical examination. Patients who have macular degeneration, they report early, whereas glaucoma patients in the early stages, they invariably they don't report. And when the visual loss is significant, then only they present to the consulting doctors. And subtle progression is very difficult to appreciate by either the patient or the doctor on clinical examination. So, glaucoma being a mystery disease, there are several unknown factors that exist in glaucoma suspects with no definite cutoff line, like for intraocular pressure, the optic disc changes, the RNFL defects, the GCL changes, gonioscopy, visual field, association of family history and systemic disease. Diagnosis requires to incorporate all for the borderline cases to start early treatment and predict the course of disease. Artificial intelligence is suited to extract information from all these data so that these data can be utilized for a particular set of patients for early diagnosis. In reality, what is happening today that we have more patients and less chair time. So we need to have a high priority checklist to ensure that nothing important is overlooked in diagnosing glaucoma. With the fact still remains that 90% of the rural and 50% of the urban population remains undiagnosed, there is a need for a robust, accurate, and fast screening method, and artificial intelligence fits the role here. As Dr. Aditya has already gone through the basic definition of artificial intelligence, just in one line, the different definition. Artificial intelligence is a science of applying computer algorithms to replicate intelligent human behavior. Machine learning, the capacity of the machine computer to learn from experience and to modify from the input. Neural network, it is just like the network, the neurons of the brain. The software is built like the network of neurons communicating with each other with multiple inputs, with a feedback loop for learning also. Deep learning, it is a class of machine learning algorithm that uses multiple layers to progressively extract higher level of information from the raw input. For example, in an image processing, the lower levels will identify the edges, whereas the higher levels will extract the concept relevant to humans such as digits, letters, and faces. It is an advanced level of a neural network. The neural network looks like this: multiple layers interconnected with each other, communicating with each other with a feedback mechanism for making corrections, and then coming out with the final outcome, which is shown in the orange. Coming to the basic important aspect of glaucoma, the intraocular pressure is one of the most important modifiable risk factor, and trends from previous data and medication is useful for artificial intelligence. In one study, um, it was evaluated from the data of Sensimet Triggerfish, which is a contact lens based device for continuous intraocular pressure monitoring. Martin et al. Used the data from 24 prospective studies of triggerfish to identify parameters associated with glaucoma patients. What we see from uh, this diagram here is that the 24-hour IOP monitoring cannot be done in all patients. So if you have got a data of multiple number of patients with IOP fluctuation, which is compared with the daytime office intraocular pressure and the 24-hour, we see that the 24-hour intraocular pressure fluctuation, which is shown in the orange, is much higher than what is shown in the blue. And this is a prospective study which was done on 32 patients. So going by this data, if you have got a pool of data, we can set 2 times for a particular patient, take those pressures at 2 points, and then we can know what the fluctuation in that particular patient can have, and that here the artificial intelligence comes into play. Optic disc photograph is the widely and the most evaluated segment of glaucoma diagnosis as far as artificial intelligence is concerned. Lee et al. Evaluated deep learning algorithms showing almost 95% sensitivity and 92% specificity. AI Aswad et al. Evaluated Pegasus system of deep learning to detect the glaucomatous optic neuropathy from color fundus photographs. It outperformed almost 5 out of 6 ophthalmologists in the study. Thompson et al. And his team used deep learning measures to measure neuroretinal rim loss from optic disc photographs. So these are few of the areas in which a lot of work is being done on artificial intelligence. Continuing with the innovations, CALP Innovations from India has released a glaucoma software which is known as RIA-G in 2016 to analyze fundus images. It uses advanced image processing algorithm to measure disc size, cup size, CD ratio, neuroretinal rim thickness, DDLS, and violation of Isn't rule. And it uses a deep learning to learn from the users in case of error in automated detection. How the artificial intelligence works in fundus photographs, it is done by pooling of data, which is labeled as glaucoma and non-glaucoma by experts. It develops a computer algorithm based on the data, which is better than the actual individual human examiner. So the lower picture shows how it is done, so that when fundus image is put into the artificial intelligence, it it makes a comparison with the pool of data, and then finally comes out with a diagnosis whether the patient has a definite glaucoma or not. What we see in the fundus picture, what the fundus photograph shows, is the color photograph which is shown in the picture, color photograph picture. But the machine segments it into pixels, and those pixels are stored in the data of glaucoma patients. Multiple data is collected, and whenever a new fundus picture is given to this data, it is converted into pixels and accordingly compared with the previous accumulated data, and it comes out with a final picture of the fundus, final assessment whether this picture has glaucoma or not. Coherence optical tomography is automatically measures the various disc size, cupping, NRR, the retinal nerve fiber thickness, the GCL thickness. Uses artificial intelligence by the process which is known as segmentation. There are various studies which have been done, and the most interesting is the study done by Ashoka et al., which evaluated a deep learning algorithm to diagnose glaucoma based on OCT for RNFL and GCL. Likewise, in the anterior segment, it uses measurement of the angle. Not lot have been done in this field, but we are very sure with the event of more data, with accumulation of more data, we'll be able to do this part also as well. One of the most important factors for glaucoma diagnosis is the visual field, and a lot of research has been done on that. A rapid and accurate interpretation of visual field is desirable. Ashoka et al. Used neural network to identify pre-perimetric fields which did not meet the Anderson's criteria. Lee et al. Evaluated CNN to differentiate glaucoma from non-glaucoma visual fields. Anderson et al. Inferred that a trained artificial neural network obtained 93% sensitivity and 91% specificity in evaluating glaucoma visual field. Bo et al. Successfully analyzed FDT perimetry data. So, just one. So when we look at these visual fields, what we see is that the regional nature of the visual field is not quantified in the present visual field that we have. We need to have more of that for early diagnosis, the kind and the nature of regional field loss at every point. For this, what was done, archetype analysis was developed by Tobias LZ from Harvard. It provides an objective and quantitative information on regional field loss. And what he found, he came out with 14 patterns of field loss. This was done on 2000 healthcare workers, uh, a retrospective study. And then finally, the pattern was given to us in 14 different shapes. And so whenever we input new fields, we can compare it with this kind of analysis. And what he found was that the um, 11th field, which is on the left lower border, was the most interesting, because as we all know that glaucoma generally, we have been taught that it affects the periphery with focal scotomas. It's not a central disease. But he found out that in 11% of the cases, the changes in the early glaucoma were in the center. And these cases was very interesting for the fact that these were seen in mostly normotensive cases. They have early visual disability and they were the rapid progressors. So this has to be taken into account. Predicting and prognosis, uh, Yusuf et al. Showed that machine learning detects visual progression fields consistently with slow progressors also. Cascade Net 5 model was able to predict future visual fields for up to 5.5 years based on a single visual field input. Kalsman et al. Could predict progression of mean deviation at a different target intraocular pressures. And all these can be helpful to guide, set up a target intraocular pressure. Future prospects. Algorithms are always getting better. We expect artificial intelligence with extremely good sensitivity and specificity in future to surpass human ophthalmologists but not replace. Combining various glaucoma evaluations can achieve a near perfect diagnosis and prognosis. Desirable, what is desirable presently is that if we have a single test to extrapolate and predict the other using artificial intelligence, that will pave way to lot of shortening of chair time and expenses for the patient also. For example, a single OCT predicting a visual field by extrapolation. So one single test can give you the field, can give you the RNFL, GCL, almost all, one in all. So 6 pearls to take home as a message is: try to make the best diagnosis, assess all major glaucoma risk factors, use all tools at your disposal. Do not underestimate life expectancy. Do not assume that glaucoma damage will only be peripheral. Do not miss a good screening opportunity. Artificial intelligence is in a transition phase. The present accuracy level can pave way to development of reliable models. Future use of artificial intelligence in the healthcare system can address the current limitation of access and timely management across the world. Thank you so much for your kind attention.
Thank you, Pranav. Here thank you for your elaborate descriptions.
And one thing I would just like to point out, that this artificial intelligence we are talking in the last 1 decade, but artificial intelligence as such in glaucoma has been widely used for a pretty long time, as long as 20-25 years from now. Because if you look at the fields, the Humphrey, the pattern, the stat pack analysis, that is also an artificial intelligence which uses to differentiate between what kind of field loss normative data compared to the present data, that comes out with an analysis whether the patient has glaucoma or not. So that stat pack analysis was started most probably in 2001. Before that, there's another aspect, the visual field index, that came into 2008 and 2009. That also predicts what percentage of field loss has taken place and what is going to happen in the next coming 5 years. So these predictions, they all are using artificial intelligence. Now the level of artificial intelligence, the application has gone up with the advent, so that with multiple sources, every source like family history, systemic disease, the intraocular pressure, the OCT finding, all combined together with a CNN network can clinch the diagnosis in early glaucoma, so that we can start treatment early. Thank you.
Thank you, Pranav. At present, the whatever the we have gadgets we have, it always there is a comparative study. It already fed previously your data, and then whatever we feed the data, it just gives the just idea. So the artificial intelligence is not the new one. It is coming since it is a Humphrey field analysis or
the
whatever the gadgets.
the best part is the learning loop.
Look,
Yeah, whatever data we have,
uh,
there is a learning loop to it. So
uh,
whatever new data is added
hmm.
to the existing data,
Yes, yes.
and the correct one, like whatever it be, the OCT or whatever, the machine learns
Machine
and then
learns, then it
modifies the entire thing from the pool of data it has collected, and then comes out with a final
final
assessment.
assessment. In India at present, there are few tools like from Remedio. It just come. It is used for screening of the uh, purposes. So for large number of cases, it is not possible to do all things in one go. So Remedio has developed artificial intelligence based algorithms, and which just with one photographs and the tonometry, it can just give an idea that patient may develop glaucoma in future. Then it is for the referral purposes for higher institute. So at present in India, artificial intelligence glaucoma is used as a screening purposes generally, not in detail for the diagnosis. It just gives an idea in the main hospital.
I think in the coming future, not only
uh,
for screening is an important tool in the
uh,
sense that what data I showed, that 90% of the rural population in India still remains undiagnosed to glaucoma.
undiagnosed.
So screening, if we can have a fast screening method which is aided by artificial intelligence, we can come to a conclusion and we can make most of the diagnosis and then refer them to a
uh,
higher center for higher
yes, for referring the higher
investigation,
investigation.
so that we do not miss. And with a lot of patients, less chair time, we need some kind of a system in which we can be fast and accurate,
Mm.
and this system really suits the
Yes,
healthcare system.
yes, it will help in future for to low down the blindness to large extent due to glaucoma.
Absolutely, early detection for any
Yes.
disease, not only eye, ophthalmology,
Okay.
cardiac, and everything, that will be
Thank,
a boon for humankind.
thank you. Our next presenter is Dr. Pranita Sahai. She will be speaking. She will be speaking on artificial intelligence and keratoconus, ectasia, and other corneal diseases.
Good morning, everyone. Unfortunately, I have a really bad voice today, so I'm going to play a recorded video. So, I'll be presenting on the topic artificial intelligence in keratoconus and other corneal diseases. I have no financial disclosures. So, as the discussion has been going on, the majority of the work in artificial intelligence and ophthalmology is pertaining to retinal diseases. However, the upcoming studies show that artificial intelligence is being explored in areas of corneal diseases, cataract, and glaucoma. In cornea, the most common areas wherein artificial intelligence is being applied to include keratoconus, refractive screening, infectious keratitis, dry eye disease, Fuchs dystrophy, pterygium, and corneal transplantation. Keratoconus and refractive screening are two of the most hot topics and most explored areas for artificial intelligence in cornea. Pentacam and OBSCAN 2 are the two conventional tests that are used for identification of keratoconus. The results of these tests are extremely sensitive and are highly predictable. However, the reports of these tests show a vast data set and require an experienced eye care professional for its analysis. So, why is AI important in keratoconus? Form frosty keratoconus identification and keratoconus progression are two most important areas in the field of keratoconus that require early detection with close monitoring and prompt treatment with corneal cross-linking to preserve vision and result in better visual outcomes. However, there's a lot of confusion while assessing the Pentacam or OBSCAN reports in FFKC identification and assessing serial reports for keratoconus progression. That is where artificial intelligence becomes handy. The data that is pre-fed into the algorithms of AI for developing softwares for keratoconus identification include refraction, imaging data of keratometry, elevation, tachymetry, heat maps, and also ocular biomechanics. The various algorithms that are used are described in this table. The most common ones are the convolutional neural networks and random forests that are used in keratoconus identification. The pentacam images are most commonly fed onto these algorithms, and ultimately these algorithms are able to identify normal versus early keratoconus and advanced keratoconus. So keratoconus identification, staging, and progression all can be done with the help of artificial intelligence. Also, prediction of visual and refractive outcomes of treatment like intracorneal ring segments has also been described with artificial intelligence. Overall, a high sensitivity and specificity has been reported for keratoconus detection with AI. Also, some studies have compared AI with non-AI indices, that is the KISA and the keratoconus index, and reported similar outcomes between the two. Keratoscreen model is one of the models that has been developed to screen early keratoconus and other ectasias using Zernick polynomial data from the corneal topography and tomography. It uses an artificial neural network. KEDOC, that is the keratoconus early detection and of progression model, uses serial pentacam reports with a deep learning neural network algorithm for detecting keratoconus progression. Manual detection of progression versus image-based detection of progression was compared in this study by Reddy et al., who found that identification of progression was earlier and CTVA was more stable in AI-based detection of keratoconus progression and interventions. An ongoing project which is being developed is the smartphone-based keratograph for identification of keratoconus. So this is like a cost-effective alternative to the expensive equipments of Pentacam and OpsCam, wherein the smartphone has been coupled with a Placido disc-based imaging, and the software is extremely user-friendly and does not require a healthcare professional for capturing images or analyzing the results. Hence, can be used for community-based surveys or screening for keratoconus. Keratoconus severity classification has also been studied by various authors using artificial intelligence. Refractive surgery is one of the most common procedures performed in ophthalmology after cataract these days. And with innumerable patients turning up for refractive surgery, it is very essential to screen these patients well to avoid long-term complication. So AI in refractive surgery helps in prognosticating visual outcome and also calculating the risk of post-LASIK ectasia, which is extremely pertinent in these cases. Pentacam Random Forest Index is one of the parameters that has been developed with artificial intelligence, which when compared with BAD, that is the Bellin-Ambrosio display, that is the conventional test for identifying risk of post-LASIK ectasia, it was found that PRFI was way better than BAD in predicting post-LASIK ectasia. Also, machine learning model was compared with conventional methods of person tissue ablation and Randleman ectasia risk scoring, and it was found that the machine learning model was better. It was correctly able to reclassify patients of post-LASIK ectasia as ectasia risk group on the basis of pre-operative data that was available and fed into these algorithms. Now, AI has also been explored in infectious keratitis, where these algorithms have been correctly been able to identify corneal ulcer and also the type of corneal ulcer. It was observed that the diagnosis with these AI-based algorithms was found to be better when compared to clinicians. Also, the specificity of these algorithms for fungal keratitis was way higher when compared to bacterial corneal ulcers. It not only identifies corneal ulcers but also assess the disease severity based on the measurement and assessment of size of the corneal ulcer. And because it is able to assess the size of the corneal ulcer, it can also assess the response to therapy, medical therapy that is being given to patients by assessing the serial clinical photograph data. Now, this is a study by Patel et al. Where they reported the measurement or assessment of size of the corneal ulcer with artificial intelligence. You can see that the ulcer was monitored serially with artificial intelligence. And in fungal keratitis, it has also been put to use for assessment of results of confocal microscopy. As you're aware, the confocal microscopy results are provided in multiple section images, and each image needs to be analyzed closely to give appropriate and good results. An automatic detection of these sections, especially when detecting hyphae in cases of fungal keratitis, can be extremely time saving and can reduce the workload of the healthcare workers. Now, various other corneal pathologies where AI is being explored are dry eye disease, wherein ASOCT images have been used to assess the thickness of the tear film. Frontal eye videos have been used to assess the tear breakup time. Tear film lipid layer interference images have been used to assess the lipid layer breakup patterns to compare to assess and diagnose evaporative dry eye when compared to aqueous deficient dry eye. In Fuchs dystrophy, deep learning algorithms have been used to identify early Fuchs dystrophy where there is only descemet endothelium complex thickening without any evidence of corneal edema. In pterygium, AI has been used to identify pterygium, its location, and also its size. Pterygium net is one of the algorithms that has been put to use for this assessment of pterygium. Some authors have also reported use of AI in assessing post-DMEC graft detachment, wherein the artificial intelligence algorithm automatically assesses the ASOCT images and identifies even minor or shallow detachments of the DMEC graft. So these are the areas where AI has been used in corneal diseases. However, the major limitation is that there are different algorithms and softwares for assessment of each of these diseases. A single software that can assess multiple diseases altogether and in the same software is something which can be most beneficial to the clinicians. A similar software was developed by Elsevier et al., where a single image of ASOCT was assessed by these deep learning neural network algorithms and identified dry eye disease, Fuchs dystrophy, and keratoconus, all three with the help of single ASOCT image. So development and refinement of such softwares in future is something which will be most promising for clinicians to use in daily practice. Thank you.
Thank you.
uh, the topic. The last part of the topic and your slide is that you can there is this algorithm has come. One picture will diagnose multiple diseases of cornea. It is very exciting. Can you highlight something?
Sure, sir. Currently, there is only one study which has reported based on ASOCT image
Mm,
on how to detect keratoconus, dry eye,
mm,
and Fuchs dystrophy. So, definitely, if we have some of these more refined softwares that can
mm,
come in, it will be really useful. But unfortunately, it is not just one imaging that can help you in identify other
mm,
all diseases. You need pentacam, slit lamp photographs. So, we need to amalgamate all these things together to develop an algorithm that can ultimately identify or categorize the patient's disease, whether it's a dystrophy, and identify the kind of dystrophy the patient has or the kind of ulcer. So, if we can put in all these slit lamp images, pentacam, and ASOCT all together, and then ultimately come with a combined software, that's going to be really helpful.
yeah. And another thing that in the diagnosis of keratoconus, you have shown that there's a distortion of eyepiece, and how it will help in how much percentage around it will be helpful if this type of algorithms comes. whether it is very high or very high accuracy or not.
Yes, so the sensitivity and specificity, as we already saw, is more than 90% with AI to detect
Mm.
form frustrae keratoconus. So definitely that is something really useful,
Mm.
because everybody who's into a refractive practice may not be a cornea specialist, may not be reading the pentacams as closely as a cornea person would do. So if they have a software handy with them in which they can just feed in the software, it's going to be really helpful both for the clinician as well as the patients.
Uh, and what about the pentacam results and your algorithms? Can it be comparable?
The pentacam algorithm, pentacam,
Pen,
pardon?
if you are using the pentacam,
Yes,
whether keratoconus diagnosis will be as accurate as your
it's better. The diagnosis is better.
yes.
The results of AI are always better compared to the human diagnosis,
Mm.
because Pentacam has innumerable values and numerical display.
Yes.
For a person to read every value very carefully is sometimes you may even miss out subtle findings. But AI is not going to miss out, because they are going to read every point set, data set is going to be taken into account.
Because it is a very important point, because we are almost many times fail to detect the keratoconus, and if it is algorithms comes with the artificial intelligence, it will diagnose very easily, and it will be helpful for the screening purposes. And also it predicts the future keratoconus uh, diseases of the, if it can develop in the patients.
A lot of
It is
patients are, it's also important for corneal ulcer, as we saw the
yes.
predictability with a doctor predicting the type of corneal ulcer
Mm.
on the basis of clinical judgment is just 60%. But the AI, the predictability is up to 90%.
Yes.
So, especially for who are non cornea surgeons, general ophthalmologists practicing in periphery, if we have a software like this and they can just feed in a photographic image, even taken with a good smartphone, and compare, put it into the algorithm, and they are given good results, the patient can be spared from the cocktail therapy that they usually receive in by the general ophthalmologist.
Okay, thank you. Thank you for your great presentation.
Thank you, sir.
Next is Dr. Abhishek Anand. He, he will be presenting on artificial intelligence and diabetic retinopathy.
So good afternoon, everyone. I think a lot of has been already spoken about regarding artificial intelligence, and I will be just emphasizing on the fact that diabetic retinopathy is one of the disease we should address with this modality. The why is that the incidence and prevalence of diabetic mellitus are increasing. Almost 10% of the world population by 2030 will be affected with diabetes, and early detection and treatment of DR remains a priority in preventing diabetes associated sight loss worldwide. There are established models of screening for diabetic retinal, and one of them is based on human grading. But it is labor intensive, requires trained human graders. Scalability is a major issue, high cost of human manpower, and there is fixed working hours. If we apply the current UK annual screening protocol globally, would require almost 2.2 billion of retinal images to be graded in 2030 itself. In this last decade, large strides have already been made in developing automated retinal analysis systems, some designed specifically to detect DR. These rely on different image analysis methods, generally based either on human designed lesion dissection algorithms or ML, or a mixture of these two broad approaches. So, if you took automated DR detection algorithm versus human grading, they do not get tired and can grade thousands of images a day and are often able to provide results within seconds to minutes of taking the photos. Scaling automated DR screening programs are furthermore largely just a matter of acquiring more hardware, and they are non-human resource dependent. uh, Whenever we are addressing any disease, we must remember that the disease itself can be addressable. The diagnosis of diabetic retinopathy is only contingent on the use of a single modality image, and that makes it one of the targets for AI. It is determined by classic morphological features in the retina, that is microorganisms, hard exudates, without the need for additional clinical data or input, making diabetic retinopathy screening highly amenable to teleophthalmology, as we have already seen, as a digital service to decentralized care. The use of artificial intelligence for diabetic retinopathy screening is based on several key factors underlying its relative success. There's a synergy between two digital innovations, the telemedicine and the artificial intelligence for diabetic retinopathy screening. And there is obviously a clear public healthcare need for diabetic retinopathy screening that cannot be met with current models of care. Now, we should see AI as an incremental technology. So there is already a foundation of telemedicine which is already established with, and we can just increment with adding artificial intelligence over it. And it is artificial intelligence should be considered as an add-on or incremental rather than an entirely disrupt. I mean, you just don't have to begin from the scratch. You can just add in. There are existing shortages in the required process resources to cater to the growing burden of diabetic mellitus patients, and which create a clear need to implement AI. Now, if you see the telemedicine, there is an overlap over it, and one of these important is the last point in which we, as a clinician, we are think that this thing will impact us. But overall, if you see in the long term, it will not be impacting our practice. It will just help you generating more patients to cater to. So you can add, you can apply it at different levels, and then you can use a protocol just for screening, then you can use a protocol just for prediction, and then you can add on for, so they can be on a multiple still levels, and then you can just filter out all those patients, and then you can address this. Now, there are a number of systems for automatic detection of DR are already available commercially, with others in the pipeline, and they are still in the early development. Nevertheless, regardless of development phase, most of these systems are still being actively developed with changes of improvements to detection of user interface, scalability, and better. US FDA, there are multiple systems which have already been approved, and whatever done and said, there has to be an adequate balance between high sensitivity and specificity for establishing a cost-effective screening programs. With lower sensitivity, more cases of DR missed, which goes against the main aim of DR screening program, the early detection of DR. And with lower specificity, a relatively large number of false positives will be pulled into the system that warrant further examination and return. So basically, you want to avoid the human grading. So this has to be balanced by a significant balance between sensitivity and the specificity. Now, these are the various algorithms of DR screening that have been done. And one of the most important challenges is the large set of retinal images on which to train and validate these algorithms is one of the biggest hurdle of developing an AI system. And there comes other questions of confidentiality, data protection, and country-specific regulations. Image data sets need to be human graded and revealed as a reference standard. And there is the publicly available Macedor 2 dataset containing over 1700 labeled written images. And this Macedor dataset has been used to validate and compare some of the studies in the past. But however, this data set contains images of excellent quality of a level that is not representative of the real life scenario. Developing DL systems against a human grading is itself a gold standard. So you can't limit the AI based on a human grader. Because we all understand that AI can go and predict beyond human grading. So once you use the reference mark as a human grading, you are self limiting the potential of AI. And automatic retinal image analysis we must understand that they will surpass that of human graders in the future. This is, however, not quantifiable if human grading is taken as the objective truth. Patient outcome based truth rather than clinician agreement to validate such AI systems have shown that it performs better than human graders. And a lot has already been spoken about AI in ophthalmology, so I will skip this. What is important is that unsupervised learning of deep learning algorithms enables them to self-learn predictive features from input data for leveled outcomes without being explicitly programmed to detect specific morphological features by experts. Therefore, their predictive capabilities are not restricted by our existing knowledge of disease phenotypes and risk factors. And just to emphasize that this is one of the image in which almost for us to detect whether it's male or female fundus, it's just like flipping a coin. But AI can detect in almost 90% case that this is a male or a female fundus. And how it is doing, we still don't understand it. The AI has implications of AI for different has been again and again emphasized with the COVID outbreak. There is certainly an economic consideration for AI, but then it will obviously surpass if you consider it regarding the public health need. There are barriers for AI adoption like cost of automated system, equipment, hardware, trained technical staff, secretarial staff. Current commercial systems require trained human grade verification, specifically with the relatively low specificity. Is AI a concern for ophthalmologists? Unlikely that we'll see a wholly automated DR screen anytime soon. Human graders will still be needed to judge atypical or low quality images, as well as for typical monitoring. Increased detection of patient requiring touchical will increment our practice rather than disrupt our practice. And deep learning can demystify many concerning risk stratification and DR management. And together we can rise. Thank you.
Thank you, Abhishek, for your great presentation.
Thank you, sir.
Now, our next presenter is Dr. Devesh Kumawat. वो CV लगा देना है. हाँ, स्टार्ट करो.
So, good morning, everyone. So, I'll be speaking about the role of AI in other retinal diseases like retinopathy of prematurity and age-related macular degeneration, and the recent facts and futures related to these topics. So, now what is the conventional approach to ROP is that we screen the babies which are at risk are screened by trained ophthalmologists as per a screening schedule, and then once a treatable ROP develops, treatment is done and the babies are then followed up for regression of the disease. So every year 2 lakh preterm infants are added to the at-risk population, and to cater to this huge number of at-risk infants, we have only 215 registered ROP trained ROP personnel in our country, which is less than 1% of the ophthalmologists in our country. And because this disease can flare up very quickly and can have an unpredictable course, we have a very strict screening schedule to follow, and it is at very short intervals. And the initial screening is done at every 2 week interval, and then depending on whether the ROP is type 1 or type 2, we modify our approach. Now, it is very simple to learn this, that type 1 ROP constitutes all of these and type 2 constitutes these, but then there is an inter-observer and intra-observer variability which is always there. So if we see this image, one may label it as a zone 1 disease, or someone else may label it as a zone 2 posterior disease. Because the junction lies at the junction of the zone 1 and zone 2 posterior in this image. And again, here there can be a confusion whether it's a zone 2 posterior disease or zone 2 anterior disease, because the ridge is falling in the zone 2 area in between the posterior and anterior part. And you can have early stage 3, which can be sometimes misinterpreted as stage 2, and only a fluorescein angiography can help you in this. But yes, there is a variability in not only inter-observer variability, but intra-observer variability is also there, because if I'm seeing this image today, I may label it as a stage 2 disease. If I'm seeing this image later on, I may sometimes label it as stage 3 disease also. And to add to the confusion, we have the IC336 grading system, which has given a continuum of the plus disease. That is, initially we had only plus, whether plus is there or not. Then in IC336 grade stage system 2, we had pre-plus added to it, and now we have continuum starting from 1 to 6, and so the variability, subjective variability, has further increased. Now, what is the current role of AI in ROP is that it is helping us in detecting ROP, in predicting severe ROP, and in monitoring the course of disease. So how does it help in detection of ROP? Like other machine learning algorithms, there are certain features that that are used for detection of ROP. So in the traditional machine learning, it's the features that we explicitly tell the machine to look at, such as the vessel tortuosity and the vessel dilatation and the zone of the disease. So the machine, based on these features, then classify it as a diseased or non-diseased subject, and then the treatment is decided. So there are various traditional machine learning tools that have been already been in use, such as ROP tool or RISA and vessel map. But more recently, we have the deep learning algorithms which can directly tell us the diagnosis without explicitly being told what to look at. So IROP DL is one of the system which has been given a breakthrough status by FDA, and I think it may be recent. It may be soon FDA approved for use, commercial use as well. So it is developed by the National Institute of Health, and it has a sensitivity and specificity of more than 90%, nearly 95%. So it is very accurately able to predict the retinopathy of prematurity. Now, another area where AI is of use is in prediction of the disease progression and regression. So, vascular severity score has come up, which can range from 1 to 9, and it can tell you on successive images whether the numerical value, is increasing or decreasing, and the disease, how is the disease progressing, or is it regressing, and based on that you can modify your treatment approach. Now you can also predict severe ROP using AI algorithms. So one of the study by Coiner et al, and they have shown that based on the images taken at 32 and 33 weeks, you can predict the risk of development of treatment requiring ROP after 1 month. So that is a very good, promising this thing of AI, that you can predict which babies are going to develop severe ROP after a duration of 1 month or so, and you can target all your resources to further screening of those babies. So this can simultaneously reduce the number of ROP examination. Think of the number of reduction in the ROP screening, the resources that could be channelized to other babies rather than screening, because not all of these at-risk babies will develop ROP. Only 5% of these will develop ROP, and out of that 5%, only 1% will require treatment. Now, the future prospects include better perinatal management using AI and primary prevention of ROP. If that can be done, then it will be a very meaningful for us. Now, it can also be used for risk prediction of the vascular arrest and reactivation following anti-VEGF therapy, because anti-VEGF therapy has become a primary tool of management in ROP these days. And vascular arrest is a common problem occurring in up to 30 to 80% of the babies treated with anti-VEGF therapy. So if we can predict which all babies are going to develop vascular arrest, then maybe we can combine them with laser therapy as well. Now, coming to ARMD, the conventional approach to treatment is management is that we identify the at-risk patients, and again, a trained retina specialist is required here, and we grade it into different severity scales, and then we manage the patients. So we have a huge disease burden in our country, and the prevalence in our country ranges from 1 to 30%, 1% being late AMD prevalence, and early AMD being as high as 30%. So there is a huge disease burden, and again, we have a limited, only 1,000 retina specialists who are registered in the Vitreoretina Society, and to cater to this demand, we are very short of the trained personnel. So ARMD grading is a simple grading system which is based on the presence of drusens and pigmentary changes and CNVM or geographic atrophy. Now, what is the current status of AI in AMD is that it is being used for detection of disease, classification of the disease, prediction of late AMD, and in disease monitoring. So there are numerous algorithms which have been developed by various authors, and until 2021 there were nearly 20 studies which had already been published using different algorithms for detection of ARMD from fundus images. And how does machine learning helps in detection, and how does it detect is basically it picks up the changes, certain specific changes that it picks up. Most likely these are the drusens and the pigmentary changes, and in OCT images also can be used by AI softwares to segment the OCT images, pick up the changes in the different layers, pick up the thickness of these layers, and then give the disease outcome. And similarly, fundus fluorescence, autofluorescence images have also been used by AI based on the amount of hypoautofluorescence, the extent of hypoautofluorescence. It can predict the progression of geographic atrophy. Now, it can also be used to predict the risk of late AMD, and in addition to the deep learning algorithm, you can combine the survival analysis. You can use the genetic information and then predict that which type of patients are more likely to develop, whether the Caucasians or the Asians, Africans, which type of patients are more likely to develop a severe disease or a late disease in future. And AI can also it also has the capability to objectively identify, locate, as well as quantify intraretinal subretinal fluid. Currently we only look at the central macular thickness and the presence of intraretinal and subretinal fluid, but here AI can quantify it and then can tell us whether the disease is progressing or it is regressing, and that could be a major boon to us. Now, the future prospects, again, the best use can be of AI is to the clinical trials, because we have tremendous amount of data that needs to be analyzed. So, multicentric studies can be performed, their images or data can be compiled, and AI can be put to use, and that could be of really great boon to us. So the challenges with AI remain the same as have been previously been told. So a reference standard is being created initially to create an algorithm. So it may have some observer variability among the experts as well. So experts may always not have very good agreement. So that is one problem which one need to cater. And we cannot generalize a algorithm which is validated, suppose in Caucasians, to our country. So whatever algorithms have been approved elsewhere, we need to validate them first in our population using our own machines, and then we can use them. And then the explainability and medical legal issues are two of the issues that still haunts us. And financial considerations are, yes, it's very expensive tools, and these have to be extremely accurate to make them into pipeline. Now, to summarize, AI-based automatic tools can substantially benefit for the diagnosis and management of retinal disorders such as ROP and ARMD. But an assistive mode should be used till we have very robust algorithms, and that too they have to be approved by the regulatory bodies. Thank you.
Thank you, Devesh, for your very excellent topic presentations. Now, next presentation will be myself. I will be talking on artificial intelligence and IOL power selection. Let's start. Yes. Good morning to everybody. My topic is IOL power selection using artificial intelligence. Purpose of this IC is to compare the accuracy of widely used IOL power calculation formula, including the artificial intelligence based formula. As you know, the artificial intelligence based formula are Hill, RBF, Leda Super, and the Kane. Regression formula most recently is Barrett, Oleson, and EVO. We have developed a lot of improvement in our expensive machines, and there are multiple formulas, but these old formulas are regression formula. It is all formulas are not very accurate, so no human can ever write a single formula that take account of every adjustment. So that's why the biometry, till now we use the decision tree to devise which formula we use for a particular cases. This is a cumbersome intuition and needs a lot of experience. This intuition is mainly due to inaccurate calculation of expected lens position. But how can we convert this intuition into the approach that is easily available and useful to less experienced surgeon? How to close to the perfect IOL power? We have Barrett formula. This is again the regression formula, but here the expected lens position is calculated very accurately, but how it is calculated, it is not known. Now another is the Oleson formula. It is also the regression formula, but is a new concept of ray tracing assisted intraocular lens power calculation. Here is the concept of C constant, which is developed as a simple method of predicting the post-operative position of intraocular lens from the pre-operative dimension of and position of the crystalline lens. Here again, it eliminates the expected lens position with K and artificial axial length and white to white. So there is no guessing because it is not related to the expected lens position. So it gives a very good result. And EVO also, it is also the regression formula. It also gives, it is based on the theory of emmetropization that generates the emmetropia factor for each eye, taking into account of optical dimension of the eye. Now, come to the artificial intelligence formula. To get the more accurate result, we have artificial intelligence calculation with two main approaches. First, using a direct artificial intelligence approach of pattern recognition. Hill RBF formula is based on this. Using on the sweet spots of multiple formula is another issue. Here we created 3D surface from the big data calculated from the sweet spots of multiple formula. And what is sweet spot? It is a place where we get the maximum correct response for a given amount of input. Because for a formula, not all the ranges of input gives the equally maximum correct response. So after creating the 3D surfaces, we enter the data and perfect results were obtained by using the artificial intelligence pattern recognition within the big data in LiDAR super formula. When we upload the data of a patient, artificial intelligence-based formula finds a distinct pattern in apparently random clouds of data points already created by a large number of cases based on the pattern recognition of artificial intelligence. Thus, it is a purely data-driven IOL power calculation approach, and therefore it is free from the limitation of expected lens position and also free from the limitation inherent to the standard formula. These are adaptive dynamic learning process and continuously becoming better and better. Here again, here it is important that here we do not use the expected lens position in the formula. So it is very accurate. It is based on the deep learning, it is already been discussed. Now, Hill RBF has, we have axial length, K reading, ACD and CCT with white to white, lens thickness, gender and ethnicity. The limitations are again inbound, the prediction value is reliable, and in prediction value is highly probability that is within 0.5 is the target outcome. Outbound, there is a limitation is called the outbound. The outbound data showing the prediction value may not match the target outcome within 0.5 and not enough data is validated. LiDAR super formula, as we said, it is creating the LiDAR super surfaces. In the X, this IOL power is shown in the Z axis, and X and axial length, and the corneal power is in X and Y axis. Now, LiDAR super formula is created by using the four formulas, that is Hofstad Q, Holiday 1, Holiday 2, 1, and with Wang Cox axial length adjustment, and Heggies, but not the Barrett. Here the section of the sweet spots of each formula based on the axial length is shown in this first figure, and second figure, all are connected, and the last, the section is amalgamated to a super surfaces that is called LiDAR super surfaces. It is the interface of LiDAR super surfaces. As soon as we enter the data in the interface, we get the correct value, and also there is a three-dimensional graph. The surgeon knows instantly if he is handling typical or is unusual eye. It is better than the Barrett super formula. Here we compare the super surfaces of both LiDAR super and the Barrett's universal formula. Here the blue area are they are over it shows the identical results, and the red area gives the not very accurate result in the Barrett universal formula. But for the LiDAR super formula, it gives extremely good result. Now, another artificial intelligence-based formula is the Keynes. A required parameter are axial length, ACD, and K-value, gender, and A constant. Accurate, and it gives a very accurate results. Now, to verify, we have gone through the retrospective studies in which data is collected. Here again, the mean numerical error is very low in the artificial intelligence-based formula. The mean absolute error also, the Hill RBF and LiDAR super, they are all artificial intelligence-based formula. They have the minimum error. And sensitivity of the formula prediction of 0.25, 0.5 by 1 and 2 gives the maximum result within 0.5 diopter of spherical equivalent. This is the same thing as for extreme eyes. Again, the artificial intelligence formula is better than the other formula because mean absolute error is smallest in these formulas. Now, for the toric calculation, we have Ladas super and Keynes formula, that is artificial intelligence based formula for the spherical part, and the Barrett toric calculator for the cylinder part. If we combine both, then we gives a very good result. For post-Lassic calculation, there is no artificial intelligence based formula till now. This is a recent study by the Cheng et al. In the Journal of Refractive Surgery. Here again it shows the Keynes formula and other artificial intelligence formula is better, and especially the regression formula, the newer one are equally comparable. So to conclude, the artificial intelligence formula is a single answer for any IOL calculation query. It is totally data-driven artificial intelligence formula pattern recognition without estimation of expected lens position. Formula should be free from the limitation of lens position estimation. Though Barrett formula is very commonly used, here the calculation of expected lens position is inbuilt and very accurate, but it is important to use newer formula that Oleson, Keynes, Hill RBF and Ladas Super. Artificial formula is continuously evolving and its accuracy is very high, it is more than 90%. So artificial formula being the game changer and is the grandmaster of biometry. Thank you for your attention. But next speaker is Dr. Sujit Misra. He will be talking on the limitation of artificial intelligence.
Thank you, Dr. J.J. Agrawal, sir, for giving me this opportunity. So I'll be talking about limitations of artificial intelligence. So what is artificial intelligence? It's a branch of computer science in which machines mimic the cognitive function of human mind. What he says, AI scares the hell out of me. And it's capable of vastly more than almost anyone knows, and the rate of improvement is exponential. And with this potential tool, the role I have been given is to tell the limitation of the brightest child of the class. So limitation always doesn't mean pointing the negatives. It's about critically analyzing so that effective improvisation can be there in the system for its better future. So if we look at this whole scenario of artificial intelligence, what we are doing, we need to have resources. Those resources undergo assimilation, and then it comes to its application, and then its impact or relevance. This is the whole scenario of artificial intelligence. And for resources, what we are looking for the data, which is dependent upon methodology of capturing, resolution of imaging, because we are talking about ophthalmology, so imaging is important. That resolution, it will vary with time depending upon the resources available for data capturing. When we went to nanoparticles, many things changed at the level we are working. So subset of information will keep changing, keep improvising with change in resolution, so will be the outcome. It's an ongoing process of improvisation till we enter the phase of consolidation. Do you think that is possible? That's an ongoing process. If you say it is consolidated, then everything is over. Information collected at microscopic level will be entirely different from what you capture at macroscopic level. And then area of interest, where you are going to use that information. So that area of interest, okay, ophthalmology, more imaging based, but will it be applicable to all the branches? That creates a big limitation in data collection. Then assimilation is analyzing available resources into meaningful tool. This needs use ambience creation to exactly simulate the recipient bed and this needs gross to subtle details of optimization. Now, regarding subset of data and its interpretation, by just few pictures, I will show you this canine and human interaction. All these pictures will show that interaction. Here also there is an interaction between human and canine. Here also there is an interaction, and here also there is an interaction. But there are a lot more beyond these pictures, which I will call data here. So it is just a collection of data and its interpretation. There is an entire world lying in between. When it comes to application, the ground zero milieu will decide whether the suggestion is practical or not. Even if the suggestion is correct, its applicability will vary from place to place, that is recipient bed. And need-based customization is the real issue. And then its relevance, what impact the customization is going to create, whether it is useful or significantly useful or not. Many a times, even if it is right, the compliance issue will come from that point of view. What is its practical significance? So many things in Indian perspective will have entirely different relevance if you compare to Western world. So we are still in the very early stage of what AI is really capable of. Many data, many informations are there. Just as a prototype with this article, I am trying to highlight various methods for use of artificial intelligence in diabetic retinopathy cases are there. And if you look at the specificity and sensitivity, then what does 90% sensitivity and 90% specificity means? 1 out of 10 cases is missed, and 1 out of 10 cases is falsely diagnosed positive. So the pool you are creating with this present tool, you will have this limitation. Someone will be missing out and someone will be aggressively chasing. So loss to one genuine patient and unnecessary addition of one unwanted patient to the disease pool. This is the meaning of this. For cost efficiency and cost effectiveness of the system, it has to be robust and foolproof. We have many tools in the form of ID, XDR, Red Marker, IART, Google. Many are there. But all the algorithms that you see, let me tell you the example of OCT. So what the consensus is, the reports of two different machines are not comparable at current level. That is the position. So retrospective versus prospective studies versus randomized control trials. There are few randomized control trials of AI system for DR to date. And metrics do not reflect the clinical applicability in these cases. And it is difficult comparing different algorithms, as I told you. Challenges in generalization to new population and settings, and logistic difficulties in implementing the AI systems. There are human barriers to AI adoption in healthcare and access and affordability. So these are the limitations that we are coming across as per the one reference I showed to you. This is another example, well known, CSME, now we call it DME. What is the message? Your definition itself is evolving. This is just one prototype. So in this ongoing process of improvisation, revision, perfection, your database is unstable. So when this database is unstable, then all the flowchart I showed is vulnerable. So with evolving understanding and modification of disease process, evaluation and management, the database has to be upgraded. Entire AI created on older understanding is at stake. So what I am saying is, artificial intelligence is a very good tool. You should use it. But make it perfect. Way back 2013, it's about, I've told many times, I heard about this femto, and I went to ESARS for hands-on training. Only one question I put to them: before jumping to the market, why you didn't fine-tune it more? Of course, this question annoyed him. But this is a question, this is a natural reaction from any person like me. When you introduce a system for its applicability, let it fully grow, let it fully mature, and then you then you utilize it across the population. So by saying that, limitation means it has to go through many phases and processes, and then later on we will have to see what is its applicability across the population. So it is essential to ensure that algorithms, data sets, and decisions are auditable, and when applied to medical care are clinically validated and explainable. Policy framework should require design of AI systems in healthcare that are informed by real world workflow and human centric designs. And lastly, it should be ensured that healthcare AI solutions align with all relevant ethical obligations from design to develop to use and to be delivered properly in the real world. Thank you very much.
Thank you, Sujit, for an excellent presentation. We should also know the limitation, though it is not put to heart. But the problem is that we should at least know the limitation. Actually, भाई सब तो बड़ाई कर रहा है, आर्टिफिशियल इंटेलिजेंस है, बहुत बड़ा चीज है, बहुत अच्छा चीज है, लेकिन उसका एक डार्क साइड भी दिखाना जरूरी है. और ये
I am really happy that you have given this important topic to me, because it is not, as I highlighted, it is not to point out the negative thing. It is for improvisation of the system that it has to be discussed.
So with this, we have the end of this IC.
Thank you.
And thankful to all of you. Thank you to all the presenters. And now we should come for the photographs.